good. I want
Mom.
I didn't. I forgot. Cody.
Is this everyone from our room?
Yeah, tomorrow will be okay.
My row's the best row. We're all.
But yeah, -5 out of 5. Maybe -1. We'll see. Yeah, get it tomorrow. That's probably last chance. All right. As I go on the homework, a couple of things. First of all, there were very few that I gave full points for as I looked at the homework. Number one. Number two, why is that? And number two, we've got to make sure. I mean, we've got 3 weeks left. There is going to be a homework grade as part of this. And so that's important. We have a test coming up on Tuesday, that derivative thing, right? The derivative test where you have to get 8 out of 10. We're going to talk more about that throughout the day and throughout the week as we go along. That's the next thing we have. And so we really have to focus in here for the next 3 weeks and work pretty hard. And I think, for example, 45, I think it's problem 45. I was looking particularly at number 45. Somebody in the other classes I was going around looking at it was apologizing to me as they were flipping because they had like 4 pages. And I said, don't apologize. In this homework, you probably should have had 4 pages, right? Now, some of you write pretty small and you got it in 2 pages. But, if you had a number 43 or a number 45, I think it was, like 1 line worth of work, and there's no way. There's no way. So I was trying to look and see what you had. And, of course, if you weren't sure what to do, then I probably should have already seen you today. At some point along the way, I did see some people at lunch, and that's good. And there were a few people there this morning too. But anyway, we need to not settle. I gave you a lot of odd problems. We need to not settle for just writing stuff down as I come around. And I really got a sense here lately that as I go around and look at those, that I'm seeing a lot of that, and that's probably not good enough. So let's make sure and do a good job working on these things. Couple of comments here. The derivative rules from before. Let's rehash those a little bit. Tomorrow we're going to write, and I'm going to give you access to a PDF of kind of a fuller list of the derivative rules. After today, we have 1 rule to learn today, but it's such an important rule. It's 1 rule, but it's probably used in almost every problem. From here on out. Not every problem, but darn close. And you'll see what that is when we get to it. But there won't be a lot left. I mean, we have a few functions to talk about tomorrow, which are the inverse trig functions, arc sine, arc cosine, arc tangent. We're going to spend a little time on those. We have another technique to do that we'll work on Thursday that happens in certain kinds of equations. But along the way, we'll still be reviewing and practicing all these other ones. And then really Friday, Monday, the weekend, there won't be anything new at that time but practice and practice and practice. And the gateway test is probably going to be about Tuesday. Okay, and that's where there's 10 problems. You have to get 8 of them right, or you keep retaking until you get 8 right. Okay, that kind of thing. Somebody in the other class asked how many pass it or get 8 right on the first try. Traditionally, it's somewhere in the 4th to a 3rd range, 25%, 33%, somewhere in that range. I mean, it's been higher. I don't think it's ever been as high as a half. I don't think there's ever been half the people get it. All right, and then there's a whole nother big percentage that just make little mistakes here and there, and then there's another group that look like they haven't done any practice at all. I shouldn't say look like, literally haven't done any practice at all, and so, or very little at all. So we want to make sure we don't have anybody in that group, hopefully. So you will have opportunities. I will give you opportunities, and matter of fact, if you want to look in your book real quick at page 195, if you would just flip back to page 195. I'm going to show you today a couple of websites that have practice problems on them. And then you look at page 195 and you can see there's a pretty good number of practice problems there as well. 195 and 196, right? And so as we get to Wednesday, Thursday, Friday into Monday, those are some of the sources we'll be using to practice problems. So as we look at what we have so far with derivative rules, we said if you have a constant setting on the outside, that it just hangs out there. And yesterday we showed how that could be thought of as a product rule, but it works out the same, but really you don't want to think of it as a product rule. You just think of it as a K on the outside. If you have something added or subtracted on the inside, we always said, well, you just leave that alone, leave the inside alone. We're going to talk more about insides today, but you just kind of leave those alone. Now we said if you have a number multiplied by the x on the inside, you got to kick that out. And again, we're going to talk today in more detail about why that happens. One that did affect us today, I noticed a few people were asking me about this, is this rule here. If you have a derivative of two or more functions that are just added together or subtracted, then we just do their individual derivative. You just do the derivative of that term or that function, and then you do the derivative of this function. Now, where does that apply? Well, that's like number 39 in the book. 39 said that, it wasn't F. What was, somebody got 39 handy there? That was the one where you had to do they said show that it was the antiderivative. Well, how do you show something's an antiderivative? Do the derivative of it, right? Was it, what do you call it, G or big G? Okay, so big G was 2 minus times cosine of x. Now, according to your order of operations, this multiplication here takes precedence over this subtraction, right? So when I go to do this derivative here, g prime of x, which of course would be little g of x, when I go to do this derivative, okay, I got f and g. This is the f function, and this is the g function right here, right? The f plus or minus g. So I'm just going to do the derivative of the 2, and then do the derivative of this. Now, when I go to do the derivative of this, I need what? I need the product rule, right? To do the derivative of this, I need the product rule. But according to this rule, I've got a function. 2 is just a function. It's a constant function, 2. Function minus a function. This rule says you do their individual derivatives. So I'm going to do the derivative of 2, which of course is 0. Now, here's where this does get a little tricky. This minus. According to this rule, you do the derivative minus the derivative. So I do 0 minus, and now I should probably put a big set of parentheses there. So the derivative of 2 is 0 minus, and then do the derivative of this as a product rule. You see what I'm saying? And then you'd have to distribute that negative. Now, here's what I would do so I avoid having to do that distributive thing there. Here's how I would think of this problem. I would think of this problem as 2 plus a negative. I'd rather think of it that way. And attach that negative there as if it was a -1. Then, if you do that, you don't have to worry about distributing that negative. Now, when I do the derivative here, I can just think, okay, the derivative of 2 is 0 plus, and now the derivative of this. Now, to do the derivative of this, that would be the u, and that would be the v for my product rule. You see what I'm saying? So now when I do the derivative of the first thing, the u prime, I just attach that -1 there as a constant out in front. And so what will happen is when I do the derivative of the first, it'll be -1 e to the 2x, then I got to kick out a 2. And then the cosine left alone, and then plus, and then I leave the u alone, I get -e to the 2x, and then the derivative of sine. But you notice how I didn't have to distribute that negative now. The negative came along on both terms because I had attached it to that first one. Okay, and then of course, derivative of sine or cosine is negative sine, and we're going to talk about that in a minute here too with this negative. But anyway, okay, and you should really finish that up and work it around, but then it does end up being equal, I think. Okay. All right. So anyway, that's that rule there. Then yeah, Cody, go ahead.
You had to say that again?
Like, you you had the e to the negative e to the 2x times 2
right?
cosine, did you take it out? Does it matter where that 2 is?
Yes, one of the things we're going to talk about today is simplifying. And here's what Cody's saying, I think. I had -1 e to the 2x, and then I kicked out a 2. And you're saying you put that together and did that. And that's absolutely necessary, yes. In your final answer, you need to do that. Yes. And as we go through the week, we'll talk about simplifying, because when you look it up in the back of the book, or you do it on your calculator to check, and you get these different versions of your answer, and you're wondering, well, which one's right? How do I know? We're going to work on that throughout the week. There's certain rearranging. To me, this is kind of rearranging, but it's also combining, and I think that's important. 2 times -1, we should combine those and make that a -2. Absolutely. Okay. So we will talk as we go through these. We'll talk about that, and if you have questions about that, be sure and ask. But my goal is by next Tuesday you have a decent grasp on what you should simplify, what doesn't need to be, and if you're in doubt, go ahead and simplify. Problem is, you got to do it right. Right? If you're trying to simplify something and you make some algebra error or mistake, that's going to cost you also. But I am going to be somewhat picky on the simplifying, especially on the first gateway test. I mean, let's think about it. You get 30 out of 30 if you pass it, and you can miss 2. Right? You can miss 2 problems and still get a 30 out of 30. So you got to earn that. Right? So there's no partial credit on it. Right? I mean, it's right or wrong. If you leave off a negative, or you forget to kick out the 2, or you just make any mistake, it's wrong. Okay? So you have to have 8 perfectly good out of 10. Now, if you're taking your 9th one, maybe nobody will be taking a 9th one, hopefully. I have had a few people go that far, and that's fine. That's okay. That's why we do it, because you need practice at it. You need to keep practicing it to get it down. Okay? But if you're taking your 5th one, your 6th one, or something like that, then I may, if you keep making that one same algebra mistake that you just can't seem to get past, I may let you off the hook at that point. We'll see how things go. But if it's the first one, or even the 2nd or 3rd one, you're going to be getting A quiz grades for those. So you do have to kind of earn that a little bit. All right. So anyway, back to the rules. We do need to get a little better at these. We got to study up on these rules, right? We've got to know the power rule, obviously. E to the x is e to the x. B to the x is natural log of b. The log, both of the log rules. Ln x is just 1 over x, but a different base. You have this. And then the trig ones. I let you off the hook last week because we were a little bit rushed there with Thanksgiving, so I told you didn't have to memorize these. Well, now you do. Okay, now we do have to have these by the gateway next week. So sine and cosine we need to know, but also tangent, cotangent, secant, and cosecant. And those were in some of the homework today. And if you'd forgotten them, they were in your notes, or you could have looked them up somewhere else as well. But so we need to know those rules. And then tomorrow we're going to add in the inverse trig and like the arc sine, arc cosine, and that kind of stuff. And then that's pretty much our list. And then yesterday we learned the product and quotient rule, and then today we're going to add this new one that kind of encompasses a lot of different things as you'll see when we do it. All right, another one I wanted to look at was number 45, like I mentioned. So let's take a look there. 45 says, is H concave up at x equals, what was it, -0.5? That's the question. How do you tell if a function is concave up? If the double prime is positive. Now, Clark and I were talking that, you could also say if h prime's increasing. The problem is it's hard to show that something's increasing. You can look at a series of numbers and say they're increasing, but that doesn't necessarily mean that in between they're increasing the whole time, unless you did some sort of number line thing or something like that. But it's harder to do an h prime number line probably on this because you're only given a graph and some other stuff. But it would be possible. But I think the more common way that people would do this one is look at when h double prime is positive. Because we can actually plug in a -0.5 and see if we get out a positive number. So that's what I was looking for most people to have. At the very least, you better have had h prime. So here's what they gave you as h of x. And it was what? X squared times f of x, right? So what I was talking about as far as your homework, if I came around and I just saw you had the answer yes, well, that obviously just came from the back of the book. Okay, now maybe you had a whole other piece of paper with a bunch of work on it. Well, you should have that out so I can see it. But you need a lot more than that. What we need is to do H double prime and see if it's positive. So before you can do H double prime, you better do H prime. Okay, so tell me what to write here. 2x, derivative of the first, times f of x left alone, plus x squared left alone, f prime of x. Okay, that's H prime. We need H double prime. How are you going to do that? Two product rule, right? I mean, because what you have here is you have a function plus a function. You see how all these rules we have, you use them now in combination. Here you have a function plus a function. So that means you do the derivative of this plus the derivative of this. Okay, well, when you go to do the derivative of this, you need a product rule. Plus the derivative of this, to do this, you need a product rule. So we have to do it twice. So derivative of the first would be 2, leave the f of x alone, plus the 2x left alone times the derivative of the first, or the second, which is f prime. Now we go over to this one and do the derivative of this. Product rule, derivative of the first is 2x, leave the f prime alone, plus the x squared left alone times f double prime of x. Right? So that is the second derivative of h. Now, we want to know what happens when x is that. So everywhere we see an x, we need to plug in a negative 0.5. So 2 times f of negative 0.5, I think it's good to write this. I suppose you wouldn't have had to, but 2 times negative 0.5 is negative 1 times f prime of negative 0.5. This one's actually the same, so that's negative 1 times f prime of negative 0.5. And then negative 0.5 squared would be 0.25. And then f double prime of negative 0.5. Okay, now we got to evaluate all that. So what's f of negative 0.5? You have an f graph, I believe. Right? What's f of negative 0.5? About 2. 2 times 2 is 4. Now we need f prime of negative 0.5. How do you get that? Tangent line. Look at the slope, right? Now, that's going to be an estimate, but usually that's good enough. Now remember, now let's go back to what we're trying to do. We're trying to see if h double prime is, no, we're trying to see if h is concave up. H double prime is positive, so we're trying to see if we get a positive answer. Well, 4 is already positive. If these other ones are all positive, it doesn't matter what they are, right? So maybe we can cross our fingers and hope that happens. And sure enough, f prime is what on there? Isn't it negative? At negative 0.5, that graph's going down. It's a parabola. It's going down. So that slope is negative. So negative times negative is going to be positive. So I don't even need to have a number there. I could estimate it and get that. That'd probably be good. And then this one's the same thing. So that's positive. Now, what about this? How do you get from an F graph, how do you get F double prime at negative 0.5? Since the F graph is a parabola, it's always concave up. What's F double prime always going to be? Positive. So F double prime is always going to be positive since it's concave up. So we don't have to estimate any number at all. 0.25 is positive. Positive times a positive is going to be positive. So sure enough, and to be honest, if this was a problem where you'd probably have to say this, you'd have to explain that, F is concave up. That's why F double prime here is positive. Here the slope's negative. Okay, but anyway, we got everything's positive. So definitely, since H double prime is positive, H is concave up. So you can see what I was saying, that if I walked around and saw you just had an answer down, that would be kind of hard to believe that you did all that in your head. Okay, all right. So 46, 47, that whole section is very similar to that. Like on 46, you would use a lot of this, like you had to use H double prime again, but you already have it worked out there, so you can use it again. On 47 and 48, you take M, which needs a quotient rule, and you work that out and plug some numbers in, right? So those are all very similar types of problems. So if you need to ask me about those later, we have some work time, whatever, you can do that, or get the answer book and look at them and whatever. I do want to look at 79 here a little bit. Talk about that one. What did they do here? What was the function called here? F something? And it was e to the x cosine x. That's it? Just that. Okay. And it asked for what? What were parts A and B? Global or local? It didn't specify, but read what it says. It says the max value. What is that? Which one is that? That's global. Global. Okay, now there's another term, I should probably throw this out here, that I know on our practice tests and stuff, and our the AP tests they use a lot, relative max. Relative maximum is the same as local maximum. And global maximum is the same as an absolute maximum. Those are some terms that are often thrown around in these. But many times they don't use the word global or absolute when they're talking about it. They just say find the max value. That's global. So we're looking for a list of candidates. So we need our endpoints, which are 0 and pi, and we need our stationary points, which is when f prime is 0. So we need to do f prime and set it equal to 0. Okay? So what is f prime? Tell me what to write. Derivative of the first times cosine left alone. Well, okay, yeah, it's going to be a minus, isn't it? It's going to be a minus, but let's go plus, and then we leave the e to the x alone times negative sine. Okay, now, take a quick little side trip here. Let me make a couple of comments about the gateway test and that whole thing about a negative right there. There have been people in the past, I hope, that will not happen this year. But there have been people in the past who have probably failed the gateway test for reasons like this. If you would write, okay, so what was it? It was e to the x cosine plus e to the x, now what did you say it was? Times negative sine x. And so they write this.
No.
I'm glad that freaked you guys out.
No.
Because what did they really write?
E to the x minus
Minus sine x. They really wrote minus. They said, oh yeah, but I had a dot there. Well, you know what? That's not a good enough dot. If you have a bigger dot, maybe. But even then, I say maybe.
Dot.
Here's why I say maybe. Because number one, that's what you should have. Okay? But also, I think that to me, this is one rearranging. I talk about rearranging is usually not that big a deal, and it usually is not. Just rearranging is usually not a big deal. Here's a case where I think rearranging is kind of a big deal. I think you should rearrange that in your final answer, and you should put that negative around there in front. Okay? And it should end up looking like that. Okay? So that's, and as we go through the week, I'm going to give you these kinds of hints about writing these things and the different things that come up. But it's going to make your life easier if you'll do that. So this does end up being a minus. Okay? And then sine x here. Okay? That's one that happens, this happens a lot on because of that derivative of cosine is negative sine. And what do we do with that negative? And it gets us in all kinds of trouble. All right, and we want to set this equal to 0. Again, something that some of you on the quiz have had some difficulty with when we're doing a max-min problem. You've got to do the derivative, and you've got to put equal 0. Okay, that's very important of why you're doing that, because you're finding stationary points. All right, now, how are we going to solve this? This should be a no calculator problem. Okay? So we're going to factor out an e to the x. Now, another thing you'll hear me say this week is that factoring is not really necessary when you're simplifying many of the time. You usually want to factor if you can then cancel something, or when you're solving an equation, which is not on the gateway test, but if you're solving an equation, then factoring is a good thing to do. All right, so now we have either e to the x is 0 or cosine x minus sine x is 0. Let's treat this one first. When is e to the x 0? Never. E to the x is a graph that looks like this. It's never 0, and so that wouldn't have any solution. Okay, what about this one? Now, this one's a little trickier. I would suggest adding the sine x over to the other side. Now there's some things you can do from here, but I think your best bet is to just stop right there and ask yourself, when does cosine equal sine? Pi over 4. Pi over 4, first quadrant. Cosine and sine are the same. They're both root 2 over 2. What about the third quadrant when they're both negative? That'd be 5 pi, right? Second, 3 pi over 4 wouldn't work because one of them's positive, cosine is negative, and sine's positive, so that wouldn't work. They wouldn't be equal there. Third quadrant, they're equal, but they says only from 0 to pi. So that means only the first two quadrants, right? So 5 pi over 4 would be another possibility, but since we're only going 0 to pi, our only one is pi 4. So that's really how you should solve that one. When does cosine equal sine? Okay? It's at 45 degrees, pi 4. Now you could divide both sides by cosine, then you'd end up with tangent equals 1, and that's at pi 4s and 5 pi 4s. But anytime you divide by an x, you run into some issues, so I try to avoid that if I can. All right, so there's our only stationary point. So now our list of candidates, we plug back into the original, right? We still got to be able to do this stuff that we learned in the last section. This is very critical stuff, this whole max-min business. So we're going to put in our endpoints, and we're going to put in our stationary point, and we're going to plug those in. Now again, this is not a part of the gateway test. The gateway test is very simply going to be 10 equations, you do the derivative. That's it. No max-min, no limits, none of that stuff. Okay? But we still have to do these things. The whole reason we're learning all these derivative rules is so we can solve these kinds of problems. Okay? That's why we're learning. So we got to keep practicing them as we go. All right, so now put a 0 into the original. It's pretty easy. E to the 0 is 1. Cosine of 0 is 1. Pi 4th, that'd be e to the pi 4th, whatever in the world that is, times cosine of pi 4th, that's root 2 over 2. So we'll deal with that in a minute. Without a calculator, I'm not sure. But I'll show you how we can reason our way through it. And then pi, so we'd have e to the pi times cosine of pi. What's cosine of pi? Negative 1. So that'd be negative e to the pi. Well, it's pretty easy to see that that's our minimum, because that's the only negative we have. Okay, so that's got to be our minimum value. And now the question is, which one of these is bigger? Pi 4th is like what? A little under 1, like 0.7 something. It's about 3/4. So e to the 0.7 something, and then square root of 2 over 2 is about 0.7 something, right? 1.4 divided by 2. So e to the, so that's 2.718. Well, I'm already getting a headache. So, so I don't know if that's bigger one. I have a feeling it is, but I'm not sure. But here's, now we didn't have to do this ever in our global max-min ones. And that's, again, because we were just getting started, and there were some things we kind of left out that I said, hey, we're going to get into some issues later on. Well, here's one right here. We want to do which one of these is bigger, and this is no calculator. How could I tell if at 0 I have an output of 1, when I move over to pi 4ths, if it's more or less? If the an F prime number line would tell me if this graph is going up or down, right? So normally we don't do an F prime number line with a global max-min, but I think it would be very helpful here. So if we take our stationary point, our pi 4ths, and do an F prime number line, I think this would be helpful. So let's put a 0, let's put a pi, and using the endpoints I think would be okay here. It will be okay. Okay, we'll talk later about when that'll be issued. And now this we're going to plug into F prime. So let's plug it in up here. Now let's do this one. So if we put a 0 in here, cosine of 0 is 1, sine of 0 is 0. E to the 0 is 1, so that'd be 1 times 1. That's positive. Actually, that's all we needed right there, isn't it? That's all we needed. So F prime is positive. This is a little bit like what part you and I were talking about earlier. If F prime is positive, we know F is increasing all the way up to pi 4ths. So if F of 0 is 1, then the output at pi 4ths has to be higher, has to be bigger, since F prime is increasing. So there's our max right there. So we didn't need a calculator to know that. We could use a combination of our number line and our list of candidates to tell what the max was. Okay? All right. So, a lot of old stuff in there. Of course, his first step was the new stuff with the product rule. All right. Let me make one more comment, and then we'll get to our new rule, and that way I can leave you some some work time here. Tangent x. We know already that the derivative of that is what? Positive, well, not positive, but just secant squared. Secant squared of x. Okay? Or actually secant of x squared is how we should say it. But anyway, that's what the derivative is. But if we wanted to do this derivative, we could rewrite this as sine x over cosine x. Did they tell you to do that in any problems? I don't think they did. They just gave it to you. So we could rewrite tangent as this and do what rule? Quotient rule. See, we can do the quotient rule. So this is one of the reasons I left this off earlier, before Thanksgiving. So you don't need to write this down if you don't want to, but let's just run through it real quick. So the quotient rule says what? Derivative of the top times the bottom left alone, top left alone, and what's the derivative of cosine? So that's going to turn that to positive, and then all over the bottom square. The top is cosine squared plus sine squared, which we hopefully remember is 1. Cosine squared plus sine squared is 1. 1 over cosine squared is secant squared. Because 1 over cosine squared is the same as 1 over cosine all squared. 1 over cosine is secant squared. So the derivative of tangent is secant squared. So you can memorize it, or you can do the quotient rule every time. I think that would be bad. That would be a bad choice. I think you should memorize it. Okay? So we could have done it as a quotient rule, and we can see where that comes from. All right. So let's add our new rule to the list. It is called the chain rule. It is called the chain rule. To the word chain, or just oh, I got you.
I know, you sound kind of disgusting. Get out of my classroom.
This links to.
We all know who the weak link is in this room.
All right, here is the chain rule. It has to do with taking the derivative of something that looks like this. F of g of x. Now your book also uses what I call the fog notation, which is kind of weird notation. I'm not sure, hardly ever see it anywhere else. That's another way of writing f of g of x. Okay, with this open circle in between. But anyway, so if you see a problem with that in it, that's what they're talking about. But f of this, how we use it, which means a function inside of a function. And another word for this is composition functions. Okay, composition. Well, that's the way most functions are. Most functions have other stuff inside. Now, we've already talked about this a little bit. We talked about it with our derivative rules back here. Okay, if you have plus or minus something in there with the x, we just leave it alone and we don't do anything with it. It just stays in there. We said if you had a number multiplied in there that we kicked out that number. But again, we left the inside alone, and that's one of the things I always told you was you always leave the inside alone. Well, as we talk about this is going to allow us to do, well, I'll just open up my calculator here. It's going to allow us to do a problem like this. If I wanted to do sine of x to the third power. Up until now, we have not been able to do these. Right? And this looks like one where you'd have to kick something out. But all we talked about is if you had a constant times the x, like a 2x or a 3x, you kick out the 2 or the 3. Any ideas what you might do here, just as a guess? Cosine of x, a great place to start was this derivative is going to be cosine of x cubed, but it almost seems too easy, like there's got to be something else there. Do you have a guess as to what you think will be there? An x cubed, maybe, or somebody in their class said an x squared because we said whenever you times by the x, so x cubed would be like x squared times x. So maybe kick out an x squared. Well, let's just let the calculator do it. Let's see.
The anticipation is ridiculous. Oh, that's cool.
That's it. Where'd the 3x squared come from? It's the derivative of what was on the inside. All right? Now, is that consistent with what we've been doing when we were kicking out the 2 before? If you have sine of 2x, we kicked out a 2. Well, why? That's the derivative of 2x. The derivative of 2x is 2. So this rule doesn't change what we were doing before. We were kicking out a 2. We just might say it different. Now, the way the book first introduced it, which I love about this book because no other book I've ever seen does it this way. Most books just do it when you learn the chain rule. But I like how our book related it back to compressing a graph. Matter of fact, I'd never, in taking calculus in high school and college and teaching calculus for 4 or 5 years before we ever got these books, I never had thought of it that way. But if you compress a graph by a factor of 2, you're going to change the slope by a factor of 2. So kicking out 2 kind of makes sense. Okay? But what does an x cubed in there do to the graph? What does all kinds of weird things. And so how does that affect the slope? Well, it depends on what x is. It depends on what x is as to what it does to the slope. But what you do is you kick out the derivative of the inside. All right, so if we're going to put the chain rule into words, it would be this. And this might be worth writing down, this is something you'll say to yourself over and over again, so eventually and matter of fact, I'll say it over and over just today, and you'll probably get it down pretty quickly. But essentially, it's a 3-step process. Take the derivative of the outer or the outside function. Okay? That's where we always start, right? Like on that last one, it was sine of x cubed, so we start by doing the derivative of sine, which is cosine. We do the derivative of the outside function, because whenever you have a composition, there's an outside and an inside. The second part of this is leave the inside alone. I think it's worth just saying as kind of one of the steps here. We take the derivative of the outer function, we leave the inside alone, and then we multiply. I guess we could still say kick out, but technically it's probably better to say multiply by the derivative of the inside. Okay, so those 3 steps are the key to the chain rule. Now, think about how powerful this is. When I say this is probably the most important rule, it's because it's probably used the most often. Anytime you have something inside of a function other than plain old x, and to be honest, it even works with x. Sine x, the derivative is cosine x times the derivative of the inside. Derivative of x is 1, right? And that's why if we had a shift, if we have an x minus 3 on the inside, what's the derivative of x minus 3? What's the derivative of x minus 3? 1, right? So that's why we didn't do anything on those shifts to the slope, because the derivative of the inside is just 1. So any function you do, you can think of as an outer function and having something on the inside. All right? And so we take the derivative outside, leave the inside alone, and then multiply by the derivative inside, and that will handle any function that has that. So now let's finish the rule. We never did write it. So on this one, f of g of x, what's the derivative of the outside? F prime. We leave the g of x alone on the inside, times g prime of x. That is The chain rule right there in symbol. In the red is what that says in words. So you're going to have some problems in the homework where maybe you have a table like you had today, or you have some problems about when's it concave up or where's it increasing or whatever, where you have to do this. Okay, you'll use this, much like we did when we did number 45 up here, where we wrote it all out. You might have something like that. Okay, it might look, well, let me just throw a couple at you here and see what you think of it. So you might have a problem where you're supposed to do the derivative of f of x squared. Right? Maybe they give you an f graph, and they want to ask if f is increasing at 3 or something. Well, if f is increasing at 3, f prime has to be positive, so you need the derivative of this. So what's the derivative of this right here? Derivative of the outside? F prime. Leave the inside alone.
Times 2x.
2x, right? Something like that. That would be it. That would be it according to the chain rule. Okay? Some issues that sometimes come up. Like with that negative that I showed you on sine x. This is another common mistake that people make. If I give you a function f, and let's say it's 2x squared minus 7x all to the third. Okay, and we want to do that derivative. Now, I don't think it's ever a good idea to FOIL out one of these to then do its derivative. I think that, now, up until today, we really had no choice. Until the chain rule, we couldn't do this derivative because we wouldn't have known what to do with that inside. Okay, now we do. Now, what's the outer function here? X cubed. Now that x sometimes confuses people because they're like, well, it's not x cubed, it's stuff cubed. Well, remember, when you talk about a function as x cubed, it could be t cubed or z cubed or German shorthair cubed. It's just something cubed. Matter of fact, tomorrow, when we write our derivative rules, we won't talk about the power rules as x to the n power anymore. Well, this is how, don't write this down yet, but this is how I'll write our power rule tomorrow. We'll use u. Because we usually don't have x to a power. We usually have stuff raised to a power, is what we usually have. Stuff. And u is in stuff, so that's why we use it. Not really, but u. So when you see this, because notice it's still an x down here. We're still doing the derivative with respect to x. So u just stands for a bunch of x's. Maybe it's a 2x squared plus 7x, like this problem. Or maybe it's an e to the x, or maybe it's a sine x, right? So this just means some stuff raised to a power. Well, what do you do in that case? You bring down the power, you leave the stuff alone, you drop the power by 1, and you times by what? The derivative of the stuff. The derivative of the inside. The u would be the inside. So when we write our power rule in our list tomorrow, we're going to start writing it this way. So what happens is in our rules, we kind of incorporate the chain rule right in there. So we say, okay, if you have some stuff raised to a power, you bring the power down in front, leave the stuff alone, drop the power by 1, and then tack on the derivative of the inside. That's what that u prime means at the end. Okay? All right, so on this one, so tell me what I would write. 3 times a quantity. And now, okay, now, a couple little hints to go along the way. This is something I see every year on the Gateway test also. You know you're supposed to bring this down. You know you're supposed to leave this alone. Now sometimes this is pretty messy in here. So you bring the 3 down and you start writing your 2x squared minus 7x and you get to here and you forget what? The 2. Because you just forget about it. You bring the 3 down, you get so busy writing this stuff, you just forget about the 2. So what I often suggest is do the outer derivative first. So bring down the 3, okay, I got some stuff, and then put your 2 before you ever fill in the inside. So you don't forget about it. So we bring down the 3 to that squared. Now we leave the inside alone. And then what? Times the derivative of the inside. Now I'm going to make a critical error here. This is what I see people do. Okay, I'm going to times by what? The derivative of the inside is I see that all the time. That's horrible. Did you times by 4x squared minus 7 there? No, you times by what? You're only timesing by the 4x squared here. Because multiplication takes precedence over subtraction. If you write it like that, that's wrong. And I don't care how big you make this dot. Right? That does not make it any better. Okay? That is still only multiplied times the 4x squared. You have to put... Okay, I made a this. I got so excited about this other stuff. Thank you. Okay? So, gosh darn it, I hate when I do that because now everything I was just saying, probably half of you didn't hear because you were saying, oh, that shouldn't be 4x squared. Right?
Oh my
Okay.
God.
Okay. My bad.
You'll have
All
to
right.
do it again.
It totally ruined the moment. Okay. So anyway, you get what I'm saying. So it is, yes, thank you. It is just 4x minus 7. But put the parentheses. Dang it. All right. Now, is there anything you need to simplify here? Let's talk about that. Could you put the 3 together with that? Yes. I don't think that's necessary, but you could take that 3 and distribute it through. You can't distribute it here because of the power. Okay, if you want to take the 3 and distribute it through, you can, but I don't think that really probably helps too much. All right. Now, if that was just a 4x sitting there, if you had 3 times some stuff squared, and then you had a 4x there, then yes, I think you should put that together, bring it around front, and make that be 12x. But I don't think taking the 3 and distributing it through is a big deal because you do have these different factors. I think that's okay. But combining that 3 and 4, I think you should do. Okay? So, again, as we go through the week, hopefully you get a sense of kind of things you should do and things maybe you don't have to do. But if you're not sure, you want to go ahead and distribute it, go ahead. Just don't mess it up when you do it. All right. That's about it, really. I think we can do the homework. I'm trying to think if there's any other kinds of scenarios. Oh, I know the one I was going to tell you about. This one right here. Remember I told you how I hate this notation? Well, here's the reason I hate this notation is for this stuff we're doing right now. What's the outer function there?
Sine.
No. Because sine squared is really sine of x quantity squared. That's what sine squared is. So the outer function is the square function. So this would start by bringing the 2 down in front, leaving the sign alone, dropping that to a 1, times the derivative of the inside, which is cosine. Okay? So whenever we see this, and you get ready to do the derivative, you've got to do this. I can't tell you how many times I see people just put cosine squared. Right? The derivative of sine squared is cosine squared. No, that's not what it is at all. Okay? It's sine quantity squared. You have to do a chain rule. It's an outside and an inside. All right. So on your homework, let's. It's 3.2 homework, so it starts on whatever page that would be, 175. All right, I let the other class go right to work, and then we had screaming and shouting and all kinds of questions going on number 1. So I thought I'd save you the agony, and save myself the agony, and just go through this with you.
No.
Well, I was going to say that. I don't agree with that. That's not necessarily true.
I'm lying. He winked at us.
All right. All right. So on page 175, problem number 1. Oh, I something else I wanted to show you here before I let you get away too far here. But number 1, A, it just says write h, which they give you this function, as a composition of f and g. So in other words, that's just saying identify which one's the outer and the inner. So if this is h on number 1, So which one's the outer function? Cosine, which is g. So this would be g of f of x. That's all they wanted you to do, right? It's identify that, hey, g is the outer function and f is the inner function, and so that's g of f of x. Then in part B, they said find the derivative of h. Okay? Well, they mean to go back up to this version here, right? And do the derivative. So do your chain rule. Derivative of cosine would be negative sine x squared, kick out a 2x, that kind of thing, right? Just do your chain rule and do the derivative. Okay, so, but they got really hung up on part A here.
Why is that on the inside?
Because f is x squared and x squared is on the inside. So cosine's on the inside. Okay? So that's all they were wanting you to do there is identify the outer and inner and then write it as a composition. That's what that means. Okay? Now, what the part I forgot to show you here, and this is not necessarily something you need to get on yet tonight and look at, but on our website, and this is where hopefully some of your practice will come. Now, page 195 has a lot of practice. You can get a lot of good practice, and maybe all you need on page 195, but on our website, down here where it says web links, okay? The first two web links are Derivative Practice 1 and Derivative Practice 2. Now, Derivative Practice 2 has some practice tests from Arizona State University for their derivative test. Practice 1's pretty easy. Practice 2 gets a little harder. Practice 3 gets a little harder yet. Now, there are some problems in there that we won't have to do. Now, it's just a PDF, so it's something you could print out. It does have a couple of interesting things that it puts here. This is number 1. This would be the easier of the ones. But I was just looking at this with the other class. Number 7 here would be a quotient rule. X squared over x squared minus 2. That would be a quotient rule. But look at number 6. It's just like it, except it's flipped. But you wouldn't want to do a quotient rule in this one. You could, but it'd be messy, and you probably would, good chance you would simplify it incorrectly. I mean, there's just a lot of opportunities for mistakes. What should you do on number 6? Well, you could bring it up or just split. I've talked about splitting them apart. I think that's a better way to do it. When you have a single denominator, split it apart. So this would be x squared over x squared minus 2 over x squared. Well, that's just 1 minus, and then this would be 2x to the negative 2, like that. Now you can just do your derivative. The derivative of that is 0. And you bring the negative 2 down here, that would be positive 4x to the negative 3, and you'd be done. So it'd be much better to do that than to do a quotient. Okay? You should get the same answer if you do it correctly. Okay? But so this has a variety of different practice, and this is what our gateway will look like. Okay? This is what ours will look like. It'll be in 2 columns over here, but it's just 10 problems. Just like this. Give you a function, you do the derivative. All right, so those are some practice ones. Now, I wouldn't get started in there yet. We've got plenty of things in the book we can do, but those are things like over the weekend, we get to Monday, we can start working on. Okay? All right, the other one, practice number 1, is this thing. This can give you almost an unlimited number of problems. You've got all these different functions you can choose from, which is nice because you can say, well, I really need some practice on logs with different bases. So you can just check that box. Also, your difficulty level, 1, 2, 3, 4, and quite nasty. Okay, so you can pick different choices. So like here would be a quotient rule, right? And I just have e to the x, sine, cosine, and ln x, just some basic ones here. And then you can skip around if you want. Here would be a really easy one. Can't believe that's a level 2. X to the 1/2, wow, that's a level 2. Now there's a chain rule right there. So sometimes you can just skip around and pick ones you think would be interesting to do. There's a chain rule. It's got a sign inside of the e to the x. Well, let's do that real quick. What do you think? I know it's hard to see. It's e to the sine x. So what's the outer function? E to the x, or when we write our rules tomorrow, we'll call that e to the u. It's e to some stuff. So what's the derivative of e to the x, or e to some stuff? It's e to the stuff times the derivative of the inside. Cosine x. Now don't put the cosine up in the power, right? It doesn't go there. It's down here. So that's it. And there wouldn't be any simplifying, anything to do. You'd just be done. Okay? So there you go. So there's a chain rule one. So this has a, and then you can type your answer in if you want. Right? Now sometimes typing it in is almost more work than doing the problem. What was that? Sine x? And I probably better, maybe I better put parentheses around that. And then what was it? Times. And then submit answer. And correct. It tells you if you're correct. So that's kind of a nice website to go and get some practice as well. Okay? All right. So anyway, we'll be doing some of that in class and working on that. All right. You can use the rest of the time now to work on your homework. 3.2.
Yeah.
Oh, and that you want to look at the nasty one? Okay. Let's see what a nasty one looks like. Yeah. Okay.
Turn it off. We're done.
The square root of cosine of e to the x all to the fifth. Well, I tell you, it does make me think of one thing. Well, listen. First of all, square root means 1/2 power. And then to the fifth, if you have 1/2 power raised to the fifth, power and a power, you do what? Multiply, right? So really, before you do this one, it would probably be best to do this. So that problem is really just that. Now, what this is though, a double chain rule. Because what we have is a function inside of a function and then that inside of another function. Well, but listen, here's how you do that. Think about how you do this. You would simply start on the outside, right? What's the rule say? Derivative of the outer function. What's the outer function? 5 stuff to the 5 halves. So what you do is you bring down 5 halves to the, you drop off 1, so that'd be 3 halves, and then you leave this stuff alone. Times, and I usually just put a big set of parentheses so I don't forget about it. Now I have to do the times the derivative of the inside. So now all I'm looking at is that right there. That's all I care about now. So what's the derivative of that? Well, it's got an outside and an inside. So we do the derivative of the outside. Negative sign. We leave the inside alone. Times the derivative of that, which is, and there you go. Now you can just rearrange. So the negative probably come over, because what we have is that, times that, times that, times that. So we could rearrange those 4 things. If you have A times B times C times D, you can rearrange them any way you want. So I would move the negative over with the 5 halves for sure, and then the rest of it I wouldn't really care how you rearrange. Okay? Yeah. So go ahead and work on your homework here, and while I enter this, and we'll see if we got it. You don't, the closure, me telling you it's right is not enough closure. Of course, I don't blame you. Now that I think about it, I don't blame you. We've already it's I don't blame you. Okay, I better put parentheses.
You're always teaching us to be careful.
Yeah. Okay. E to the x times what I got? Sine times cosine e to the x raised to the, darn it, 3 halves. Is that it? Submit answer. Yes! All right. Okay. And the nice thing about this website is, as long as you enter it in any form that is equivalent to the right answer, it will do it. I think it puts down what you typed in, but like I said, I could have typed it in just like that, and it would have also said correct, right? I mean, because it can read the various, or it actually calculates and simplifies your answer to see if it's right.
So on that scale, is our gateway test going
No. I would say you would not have one. Well, that one wasn't that bad. I mean, really, no, it wasn't. I mean, by the time we get there, that's not that bad. Yeah, we definitely having a double chain rule is a possibility. Absolutely. So that one wasn't very bad at all, really. Some of these others are quite nasty, but but if we had an easy, medium, and hard range on the gateway test, that would probably be in the hard category just because it's a double chain rule. Right. So.
I had a question on doing the derivative of x.
Well, derivative of x is just one.
It's just one. Okay, so that's okay. That's
Yeah, I mean you can, but
Is it okay if I leave it like this, or should I?
No, you should make that a -2. 2 times 1 is 2, and negative, and so -2. Right. But you didn't do the derivative of the inside. The inside is not x. The inside is a cosine. This is the inside. Because your function is something square. So this is the inside, the stuff that's square.
It's kind of treated as a double chain.
Yeah, it's not. If you're going to treat everyone that just has an x in it as another chain rule, then you're going to drive yourself crazy.
Yeah. So
If it's just got an x in it, just don't worry about it. It's just,
So, yeah. That,
yeah. I mean, you're going to go nuts, yeah. Well, no, because you got to do the derivative of the inside. You bring the 2 down, drop that to a 1. Yeah, see, what you're forgetting is they leave the inside alone. You're forgetting to leave the inside alone. Look.
Oh, yeah, then you
Okay, it's 3 steps.
You can come
It's the
to that
derivative of
house.
the outside, which is 2, right? That's the derivative of the outside. Leave the inside alone. Next step. Times derivative of the inside. Negative sine x. Then you bring,
skipping steps.
there you go.
I was just gonna write another one.
I actually